Hello and welcome. In this video we will construct an efficient frontier in Python. The efficient frontier is a cornerstone of modern portfolio theory and is just a graph representing portfolios that maximize expected returns for an assumed risk profile. Why should you care about this topic? Modern portfolio theory is often applied in quantitative investment strategies and could also be helpful for optimizing your own portfolio. This video could also be interesting for data scientists as we will apply some algebra, use important Python libraries and additional resource stuff, so be sure to stay tuned. As this is a technical implementation video, I will link some helpful resources in the video description for conceptual understanding. Last words before we are starting: if my videos add value for you, you're enjoying my videos or just like my perfect accent-free English, please be so kind supporting this channel by liking, commenting and subscribing. Thank you very much in advance and shoutouts to all supporting this channel, always such a pleasure for me. Okay, let's get started with importing some necessary libraries. We need Y-Finance to get stock prices from the internet, and we also need NumPy for some calculations here. So let's execute that. And now we're getting stock prices with yf.download, and I'm just taking Apple here and Caterpillar, so these are just the ticker symbols of those stocks. Now I have to specify a time horizon, and I'm just going 20 years back. So I'm starting in the beginning of December in the year 2000 here, and I'm going until December 2020 here, okay? So we will store that data in a data frame, which I'm just calling df here. And let's just print that out. As you see, we're getting a pretty messy data frame, and I'm just interested in the adjusted close price, and out of that I want to calculate daily returns, and I want to normalize them. So I'm just using df equals to taking the log function of numpy, then just taking 1 plus df and the adjusted close price, and I'm taking the PCT change function for the returns. So if we're executing that and print out df again, as you see, we are getting a data frame containing the normalized daily returns of Apple and Caterpillar here. So the next step is to calculate the portfolio return out of that. So as you see, this is the formula for a 2-asset portfolio. So we are taking the weight of the first asset times mu, and mu is just the mean return of this asset. Same for the second asset here. So yeah, the most intuitive way would just be to apply this formula. Therefore we need some weights. So we're just defining two weights here. So we are just assuming that we have equal weights. So we have the same share of Apple and Caterpillar stocks in our portfolio. Let's execute that. And now we are just applying this formula here, right? So I'm just taking weights, axis, the very first weight here, and multiply that by df.apple.mean. So this is the mean return of Apple, and add the second weight. So that is weights 1 times df.cat.mean here, and with that I've calculated my portfolio return. Is this a good way to calculate the portfolio return? Well, it depends. For now it's okay, but imagine you have like 10 stocks, 100 stocks. That would be not good, right? So we need to find a scalable way to calculate our portfolio return, because in the end of this video, we will also show the efficient frontier for 3 or more assets here. So how can we do that? Well, we can use some algebra. So we can take the dot product. So we are using np dot dot, and then we are just taking the mean returns. So mean returns of all assets in the data frame. So that would be Apple and Caterpillar in this case. And we're also taking the weights list here. This could also be an NumPy array. And if we're executing that, as you see, we're getting the exact same results. And the cool thing about this one here is that, as already said, this is scalable. So you can use a huge amount of assets here and you're not limited, and don't have to use a not so handy formula like this one here. Now let's create a function out of that, which doesn't make sense right now, but it will in some seconds. So I'm just making a function out of that, which is providing me the portfolio return given a weight array or weight list. So I'm just using portfolio return with the argument weights, and inside this function I'm just returning the dot product out of the data frame, means, and the weights which I'm providing when calling this function. So let's execute that, and I'm just showing how this is working. So I'm just calling this function by typing down its name and providing the weights list here, or the weights array, as the argument, and I'm getting the portfolio return here, right? So this is just the functional way of what I've just shown you. Okay, I think we got that. We've defined a portfolio return function here, which is actually scalable. And now we want to calculate the portfolio variance. And as above, we are starting with an intuitive way, so we are just applying this plain formula here. So we need the weights, we need the variance of the assets, and we need the covariance of the assets. So, well, how can we achieve that in a pretty good way? We can just use the covariance function. By the way, I've explained that in another video on my channel. I'm not quite sure what's the name right now. I think it's correlation and covariance metrics of stock returns or something like that. I will link that in the video description. Nevertheless, let's calculate the portfolio variance. So I'm just calling that PV here. And just as a quick explanation, the covariance matrix is working like this. So this one here is the apple variance, okay? And this one here is the caterpillar variance. And this value, so both values, which are the same, is the covariance between apple and caterpillar. So we can just use this covariance matrix to get all those three values here. So the variance of the first asset, the variance of the second one, and the covariance of both assets. So we are starting with the first weight, which just weights 0. So this one here, as you remember, and I'm squaring that as the weights have to be squared here. And I'm multiplying that with the variance of the first asset. So that would be this value here, and I'm just accessing this value by df conf and take the ilog function, and I'm just searching for the value in the very first row and very first column, which is just this value here, okay? So maybe you have a better way, but I'm just showing you how you can apply this formula in a not so good way, but in a way which is pretty easy to understand, at least in my opinion. Same for the second weight. So we are taking the second weight by weights 1 here, so this is this value here, and square that, of course, and we are multiplying that with the variance of the second asset. So we are just taking our covariance matrix again, use our ilog function, and now we are taking this value here, which is the variance of caterpillar, and this is just ilog and then 1 and 1, because we are taking the second row and second column here, this value, okay? What else? Where am I? Here. Okay, so now I'm adding 2 times weights 0 times weights 1, and now I need the covariance of the 2 assets, so I can either take this value or this value, doesn't make a difference as they are the same. So I'm just taking df.conf and take ilog, and I'm just taking the first row here and the second column. Okay, with that, let me double check quickly. Should we write? With that, I've calculated my portfolio variance. So let's print that out. So this is my portfolio variance here. And yeah, to get my portfolio standard deviation, which is accounting for the risk, I'm just taking the square root out of the portfolio variance here. Okay, so this is the portfolio standard deviation. As above, is this a good way? Of course it isn't, as you just saw, right? Maybe you have a better way to calculate that, but this is kind of tough, right? This is not handy. So we can use an algebraic approach to do the exact same thing here. So again, we need the dot product out of NumPy. So we're using np dot. And now we are using the covariance matrix and the weights. The result of this dot product is again taken into consideration of another dot product. And now we are again taking the weights. So I cannot explain that, well I can, but this will take too much time. How the calculation is working in specific, you can do that by hand. It will make sense for you. If you have any problems with those calculations, if you cannot understand them, just drop me a comment. I'm very happy to help, but I won't explain that right now here. So just calculate the dot product out of this matrix and this vector here, and then the result of that, you're taking that and again the weights vector. So again, if you have problems with that, just drop me a comment, okay? So as you see, we are getting the exact same value again. So this is the portfolio variance, and if we are taking the square root out of that, we are getting the portfolio standard deviation, okay? As above, we are making a function out of that. So we are defining portfolio standard deviation. Again, take the weights as the argument, and we're just returning this value here. One more thing, what we gotta do is we have to annualize those standard deviations, and we can just multiply that by np square root and take 250 trading days, as we have daily values here. Okay, so let's execute that and let's annualize this quickly to have a comparison if we got everything right here. So we're getting this annualized standard deviation here, and if we're calling this function portfolio standard deviation with our weights, we're getting the exact same value. So this is fine, right? In the next step, I'm creating random portfolio weights. There are other possibilities. For example, you could define your own portfolio weights with the advantage that you can, for example, use short sales. So if you have no idea what I'm talking about, just don't worry about it. But if you're interested in how you would, for example, negative weight an asset, just drop me a comment. There are ways to do that, but I'm not covering that in this video. I'm just creating random weights here. So I'm just defining a function, which I'm just calling weights creator, which is taking our data frame as the argument. Inside this function, I'm defining a variable, which I'm just calling rand for random, and I'm using the NumPy library, take random to create random numbers here, or a random array to be more specific. And I'm just taking the length of our columns here. So why am I doing that? Well, this is scalable, right? So if I have more columns in my data frame, this is creating more random weights, right? So this is why I'm just taking the columns here and the length of that. So in our case, this would just be 2, as we have 2 columns here, apple and cat, so that would create 2 random weights. What I also have to do is to do the following thing. I have to divide that by the sum of this variable. Why do I have to do that? Because the sum of my weights in this created array should be 1. Otherwise, this won't work, as the sum of the weights in a portfolio must always be 1, right? So I'm just returning this variable, and I'm executing that, and let me just quickly show you how this is working. So if I'm calling this function, I'm just getting an array with random weights. So as you see here, this is telling me to weight 53% in Apple stocks and 46% in Caterpillar stocks. If I'm executing that again, I'm getting other weights here, right? So as you see, now I'm getting 34 in Apple and 65 in Caterpillar, and so on. So always, when I'm calling this function, I'm getting another array of weights. Okay? In the next step, we are starting to build our efficient frontier by just creating multiple weights, and we are just using those weights to calculate both our portfolio return with our function above and our portfolio standard deviation. Okay, so how can I do that? I'm just defining an empty list here, which I'm calling means. Or no, let's call that returns. That's better. And we are also taking an empty list for standard deviations and also for our weights, which I'm just calling W here. Now I'm just using a loop for I in range. Let's just take 500 here. So we are just looping through 500 iterations here. And inside this loop, I'm defining the following. My weights should just be the function call. So that I'm getting, for every iteration, I'm getting a new pair of weights here. So I can just call my weights creator function with df as the argument, and I'm just getting 500 different weight arrays here. What I'm also doing here is to use this empty returns list, and I'm just appending my portfolio return function. So I'm just calling that here, portfolio return. This is just this function, which we have defined above. And I'm taking the weights as the argument as defined above. Same logic for the standard deviations. I'm just using our portfolio SCD function, which we have defined above here. I'm taking the weights as the argument. Also, I'm interested in what exact weights I've used, so I'm just appending the weights to my W list here. Okay, so let's run that. And now we have everything what we need to plot the efficient frontier. So, I mean, we could print out the returns, so you're just getting 500 different returns here, or print out the standard deviation, so we're getting multiples, or not multiple, but 500 standard deviations here, but you can check that on your own. That is not important right now. One thing, what we need is the matplotlib library to actually plot our efficient frontier. So we're just using import matplotlib.pyplot as plt. And now we're using plt.scatter, and we are taking the standard deviations as our x-axis and the returns as our y-axis. Yeah, let's use the title to make it a bit more meaningful, which is the efficient frontier. What else can we take? We can define our x label as the portfolio standard deviation or risk. So the portfolio standard deviation is the risk, which is on our x-axis. And we're also defining the y label as our portfolio return. And yeah, let's plot that to see what we got. And now we see this beautiful efficient frontier here, right? So let's add some stuff to this graph that we can better interpret that. First, I want to just plot, so this is Caterpillar alone, and this is Apple alone. So we could plot those points in this graph, would be more or better understandable, I think. So we're just adding plt.scatter, and now we're just using df.scd.ilog, and I'm just taking the very first asset, which would be Apple, and I actually have to annualize that as well, otherwise it won't make sense. And I'm also taking the return, so I'm just taking the mean return here. search for the first asset. And what can we take for Apple? Let's just take black for Apple. And same thing for Caterpillar. So we are just demanding ilog1 here. And let's take yellow for Caterpillar. And let's plot that again. And now, as you see here, this is Apple, right? The black dot here, and this is Caterpillar as the yellow dot. And the cool thing now is we can pretty nicely interpret that. So if you just would have bought Caterpillar, this would be a bad decision, as for the same level of risk, which is the portfolio standard deviation, this is the risk. For the same level of risk, you would get, so you're just going a straight line above here, you would get a portfolio with a way higher return. And you're not increasing your risk. You're on the same level of risk here and getting a way better return. So what exactly is the efficient frontier? These are all dots above the so-called minimum variance portfolio. This is just the portfolio with the least variance or the least standard deviation. Doesn't make a difference. So how do we find the minimum variance portfolio? We are just using the min function to find the minimum in the standard deviations list. So we are getting this value, and we know that the corresponding portfolio return value is at the same index as this value is in the standard deviations list. So we can just use standard deviations, take index, and just index for the minimum here. So we are getting index 18. So at index 18, we are getting the return value. So we can just use returns and then just index for this one here. So we are getting the return for the minimum variance portfolio. And with those two values, so the return and the minimum standard deviation, we can plot that point in this graph here. So we're just adding a line here, use PLT scatter. And now for the x-axis, we are just taking min and the standard deviations. And for the y-axis, we are just taking this syntax here, so we can just copy paste that here, right? And we are specifying a color. Well, what color can we take? Green, is green visible? Yeah, I think you can see that, right? So we got our minimum variance portfolio right here, okay? And again, to buy a portfolio which is below this minimum variance portfolio wouldn't make much sense, as you could get a portfolio with a better return for the same level of risk. So from this point on until the end of this graph.
Now in the last part, let us do that for more than two assets. And the cool thing is we already made that scalable, so we just have to add an asset to our online request. Additionally, we have to amend those two lines of code here. So, I mean, you can add those assets which you are adding to your online request, but I'm just getting rid of those two lines here for simplicity. So either you take all or you take none here. So let's plot that again. So now we have our efficient frontier. And now let's scroll to the top. And as you see, I already got rid of the function calls here and all the stuff we don't need. So right now you should only have the portfolio return function, the portfolio standard deviation function, the weights creator function, and the loop here, and of course the visualization. And with that, you can just add an asset here. So for example, let's just take Tesla. Okay, now we can just restart and run all cells. And with that, we will get the efficient frontier of 3 assets. So, I mean, you can add more than 3 assets if you want. So you can play a bit around with that, right? yeah, that's it for this video. As always, if you have any questions, please don't hesitate to drop me a comment. I'm really happy to help. And yeah, if you like this video, please subscribe to the channel and like this video and comment your thoughts below. And I'm really looking forward to seeing the upcoming videos. See you next time. Bye bye.